Hello students, my name is Shashank Checker and today is the second part of the chapter Biomolecule. So yesterday we have started the introductory part where we have seen what is monosaccharides. We have not seen any examples yet for the say carbohydrates. So today we will see the examples of carbohydrate. So we will see various examples starting from glucose. We will also see the distribution of glucose into alpha and beta. So let us start our today's class. So the chapter will be including this many topics. So if I talk about the topics that will be covered today according to the syllabus, so these are the topics that we have already covered. So we have seen the classification. We have seen classification on various bases, although it is not mentioned in syllabus, but you will see that this also will be covered later on the syllabus. Then we have seen what is monosaccharides. We have not seen any example of monosaccharides, so we'll see those. So we have examples like glucose and fructose. As I have told you yesterday that you should be aware about the Fisher configuration to study more properly, or I would say to get more a clear picture of what the structure of glucose and fructose looks like. Okay, so I have given you a brief overview for that, but still you need to get a quick grasp so that you can cover that. Yeah. So talking about today's class, so we will see glucose. Okay, so we'll focus mainly on glucose. So these are the topics, subtopics that are to be covered under glucose. First, we will see what a glucose is, what is the physical property, what is the physical state of glucose, and what are the molecular masses and all. Then we will move to preparation of glucose. The various preparation methods are available for various chemicals. Similarly, glucose has also some preparatory methods that are used in the labs. So we will see those. After that, we will see some chemical reaction of glucose. So I would say that today's lecture will mostly move around this chemical reaction. So it will be the center. Okay. So let us start with what is glucose. So first of all, we have seen the classification of our carbohydrates on two bases. The first basis, I'm talking only about two bases. Today, I'm not discussing about the third one, that is the basis of hydrolysis. I'm talking about the two bases. The first basis was the position of the carbonyl center. So if the position of the carbonyl center in the Fisher projection, in the proper Fisher projection, is on the top at the first position, then we will call it as aldose. Else, if it is on the second position, we will call it as ketose. This was the first classification. The second classification was on the basis of the number of carbon atoms. So if it is containing one carbon atom, we have monos, then we have dios, trios. So mostly the examples are from trios, tetros and hexos, pentos and hexos. We do not have any such examples from monos or dios. There is no such terminology also. Clear? So talking about those, so we have say trios, we have tetros, we have pentos, then we have hexos. So glucose falls under hexos and it falls under aldose. So in these two classifications, glucose falls under aldose in case of the position of carbonyl center, and for the number of carbon atom, it falls under hexose. So it can be characterized as aldohexose. Okay, so from aldose comes the aldo, and from hexose comes the hexose. So we call it as a aldohexose. Now it is also sometimes termed as dextrose. So this dextrose is coming from the rotation, optical rotation. So you must have studied in the chapter hello alkane and hello arene what is dextrorotatory, what is levorotatory. If not, I would just give you a brief overview. So if a optically active compound is present and you pass a plane polarized light or PPL through it, then you will find that if it is optically active given, then it can rotate light in two directions. So that rotation can be towards, I would not say rotation, I would say bending more appropriately. So it bends the light towards certain angle. So if you see along the direction of say the plane polarized light from the source side, if you see, and if you see that light is bending left, okay, if the light is bending left, then it is levorotatory, and if it is bending right, then it is called as dextrorotatory. So in that sense, the glucose is dextrose. Clear? Now what is the boiling point of glucose? It is 294.8 degree Fahrenheit, and in Celsius it is 146 degrees Celsius. So it has a very sharp boiling point, I would say. The reason behind it is very clear, because it is a crystalline solid. So it would have a arranged order of, say, structure that is attributing to its sharp melting point, boiling point and melting point. Sorry, boiling point. Yeah. Then talking about the melting point, it is, say, minus 50 degrees Celsius as 760 mmHg, or 1 bar pressure, I would also say 1 atm pressure. So why is this pressure written? So the reason behind the pressure mentioning is that, because you must have seen that if we have a different pressure, then the melting point of the substance changes. Right? What is the reason behind it? The reason behind it is the colligative property. You must have heard the definition that the melting point depends upon the vapor pressure. Why? Because it is that pressure at which the vapor pressure of the solid is equals to the vapor pressure of the liquid. So if your vapor pressure around the atmosphere is more, then you would require more heat to increase its pressure to that point. Clear? So for that reason, you must mention the pressure. Then talking about its molecular formula, it is C6H12O6. This is its molecular formula. So if I ask you what is the empirical formula, what you have to say? So you will take the common ratio. Then it will be CH6O. Yeah. So this will be the empirical formula. How did I found out? I took the common factor among it. So it will be 6. So the 6 is removed. 6 2 is 12. Oh, sorry. It will be 6 2 here. Yeah. CH2O. So this will be the empirical formula. Then it has a density of 1.4 gram per centimeter cube. You can try to convert this also in decimeter cube. That is in the liter. So it will be 1.54. So centimeter into decimeter, millicenti, it will be 1.5 into 10 to the power 3 gram per decimeter cube. Or you would say liter. So I have converted it in liter because it is the most used notation. Then we have the molecular weight of 186.16 gram per mg. I will not say mg, it will be mole. Sorry, gram per mole. So how it is so? So we have 6 carbons, 12 6 is 72, 12 hydrogens, and we have this 6 sorry, it will be 12 6, yeah, and it is hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen. So carbon, nitrogen, oxygen. So it will be 6 7 8 16, yeah. So 18 6, yeah, 48 616 14 108. So if you add all these, 8 to 10, 12, 1 carry, 7 to 9, and 1. Okay, we have some mistake here. No problem. Let us see it again. 12 6 is 72. Hydrogen is 12, so 12. And 18 is the, say this is for a 6 7 8 8 to just 16. Okay, yeah. 6 is the 36, which will be 96. 6 4 10. 9 1 10 1 17. Okay, yeah. So I think it is written wrong. It will be 170 gram per mole. So this is the first connectivity structure of glucose that was initially proposed. So if you expand it, it would look like this: CHO, then we have CHOH, or I would write CH2O. I'm not defining the stereo right now, as it would be very more to handle. So let us just see the structure. Yeah. So this will be the expanded structure. Now, if I talk about this connectivity, it would be one H here and one OH here. So similarly, here will be OH and H. So this was about the initial introductory thing about glucose. So what we have learned, first of all, it is an aldose because the position of the carbonyl center is at the first position. So it is an aldose, and there are 6 carbons in it. You can see, you can count here. 1 2 3 4 5 6. So it is hexose. So it falls under the characterization that is aldohexose, and it is dextrorotatory, so it is a dextrose. Then after that, it has a very sharp boiling point and a melting point of minus 50 degrees Celsius at 760 mmHg. That would be 1 atm or 1 bar, I would say. Then it has a molecular formula of C6H12O6. Okay, it has a molecular formula of C6H12O6. This will be 180. Yeah, final. This is the final one, 180 gram per mole. It has a density of 1.54 gram per centimeter cube, or 1.5 into 10 to the power 3 gram per liter. Clear? And this is the first connectivity structure. We have not defined the position of the H and OH. This is not the accurate picture projection of the glucose. Now, let us see the preparation of glucose, how it is prepared. The first one is from the sucrose, that is the cane sugar. Cane sugar means the sugar cane, I would say. The sugar that is present in cane is called as the cane sugar. Ganna, that word if you have not heard. Now, the boiling source. Now, what is done is that we boil the sucrose with HCl and H2SO4 in alcoholic solution. Then what do we get? We get glucose and fructose, both. We get both glucose and fructose. So what are we doing here? First of all, we are hydrolyzing this. Okay, we are doing the hydrolysis of this cane sugar. It is a disaccharide. Can we say that your sucrose is a disaccharide? Why it is a disaccharide? Because it has 2 units of monosaccharides, 1 unit of glucose and 1 unit of fructose. So therefore it is a disaccharide. Now both of these are produced in equal proportion upon the hydrolysis, or I would say acidic hydrolysis of the sucrose. Clear? We can use any acid, HCl or H2SO4. The source of H plus can be either of them, and we get the equal proportion of glucose and fructose. Now do not consider them as same, because as their molecular formula is same, still they are very different from each other. Talking about the physical structure, physical properties, chemical properties, all would be different because its structure is very different from each other. Now, this was the first method. Now, if I talk about the industrial method, then in that case, it is prepared from a starch. Starch, you must have heard this in the sugar and non-sugar. So it is a type of non-sugar, and it is a polysaccharide because it can be hydrolyzed into multiple units. So when you boil this starch in dilute H2SO4 at 393 Kelvin, then you will get N moles of C6H12O6. So it is not defined. Okay, this is not defined. This N is not defined. It can be of any length depending upon the say where it is being available, from where it is being taken. That would define the length of this N. Clear? So starch or cellulose is N units of C6H12O5, and when it is hydrolyzed, hydrolysis is done in the presence of water and H plus at high temperature and high pressure. So 2 to 3 bar pressure is very high, considered to very high. Then we get N moles of glucose. Okay, N mole of glucose. Now we will see the chemical reaction. So we have seen the preparatory method. So there were two. First was from the sucrose, in which we did the hydrolysis in the presence of H plus, and we got glucose and fructose. So why I'm telling it again and again? Because biomolecule is something that you should try to memorize a little bit, because it would make things easier. Because to draw the structure each time and determine or do the reactions and push the arrows and take out the product each time is quite difficult to follow. So therefore, I would suggest you that from the exam point of view, you should try to memorize the products, that which say carbohydrate on a hydrolysis which gives which type of products. Clear? So this was about hydrolysis of sucrose and hydrolysis of starch and cellulose. Now when you will see the structure of starch and cellulose and sucrose, you will find that the glucose that is produced will also be different. So what is the difference? That will depend upon, again, the stereochemistry of a certain position in the glucose. So we'll look up on it later on. So we were in the chemical reaction. So what are the chemical reactions that can be done? to on say glucose. So first of all, we have done the reduction. How we have done the reduction? So what we have taken is that we have taken a glucose. We have taken a glucose and heated it with HI. Okay, heated it with HI. Then what do we get? We get a chain of hexane. Now, if I ask you, in what way it can be used again, this method can be used again. So it can be used to say know the number of carbon atoms present in this say given carbohydrate. How? So if you see here, we are reducing it. So the moles of HI that are consumed in the reduction of say this glucose would define the number of carbon atom that is present in the given carbohydrate. Clear? So it is a reduction reaction. And how it is a reduction reaction? We can see here that we are reducing the oxygen count. So here initially we have 1, 2 and 6. 6 high oxygens are present, and in this product we have no such high oxygens because all of them have been removed by, or you can say reduced by HI, and H has been inserted in it. So we got a normal hexane and a straight chain also. Why a straight chain? Because your glucose is also a straight chain. Clear? Then moving on to the next reaction, it is also a reduction reaction, but it is with oxime. This structure is called NH2OH. So it looks like this, NH2OH. So it is not the actual shape. It would be pyramidal only. Clear? Now if I try to reduce it with NH2OH, then I will get NOH. How are we getting it? So if I talk about the mechanism here, so we have CHO, then we have 4 units of CHOH, then we have CH2OH. Now if you see here, so if I would have expanded it, then it the carbon, it is present in the most reduced form. I would not say the most reduced form, but still one of the most reduced form because it is present as alcohol. Clear? So this is also alcohol, and this all 4 carbons are also alcohol. So the only carbon that can be reduced is this. Now what are we reacting it with? We are reacting it with NH2OH. So how it will react? So let us define it in the more proper way so that you do not get confused. Suppose I am representing all of this, say all of this down part with R. Then how it can be written? RCHO plus NH2OH. Now what are the possible reactions that we can have? If you are looking at this reaction and you are saying that it has the possibility of acting as a base, then you are wrong in this. Okay, so it is not a base. Sorry, it is not an acid first of all. Okay, it is not a acid first of all, and it is also not a proper base to react with this RHOH because it is not strong enough. Clear? So then what it can act as, so since it is a weak base, also a weak acid at the same time, but it has lone pair. This has lone pair. Now lone pairs are nothing but electrons and they're negatively charged, so they must be positive loving, or you can say nucleophile. So this nitrogen will clearly attack here and the pi bond will move upside. This will create this kind of structure, O minus NHOH, and here H. Now we will have a positive charge on this. Now since the electrically neutral molecule are more stable, so this H will just be transferred from here to here, interproton transfer, and will create OH NHOH. Now this structure that is available here is not that much stable because carbon double bond oxygen is often preferred upon this kind of structure. So what will happen? What will happen? So in this case, we have our H here, and we have also released our H2O. What will happen? This H will be transferred here. There again will be an inter proton transfer from here to here, and H, this will create a negative charge on it. Now this negative charge will move here, and since this oxygen has positive charge, it will kick this out, and finally it will form this thing, RNH RCNOH. Now if you put back R here, you will get this thing, that is RNOH, and added a molecule of hydrogen cyanide. Now similarly, we can do it same. We can do the same with HCN. How? So again, I am drawing the simplest structure, our RCHO, and let us react it with HCN. Now this H plus, it is an acid. It will give the proton here, and the Cn minus that will be available will attack here. This will have a positive charge because of the removal of electron, and now the pi electrons will move on this oxygen to neutralize the positive charge. This will create ROH, Cn, and H. So this will be the formed product, or we can write it in this way also, CH, CnOH. So what they have done, they have written this in this way, nothing new, and R is in the down, so this is the R. So what type of reactions are we doing here? What is the reaction? In which category does this reaction fall? Like this falls in oxidation. This falls under nucleophilic addition. Now if I ask you what further reactions, sorry for writing it in the bad way, means you must have understood is nucleophilic addition. Now if I ask you that what can be done further with this product, so we have a cyanide here, we have a cyanide group here. So if we hydrolyze it in the acidic condition, then this cyanide will be converted into C-double-OH. So this is a possible reaction that you can think of. Then I would suggest you that you must be eager about the further product that can be formed, or you must try these things. Okay, clear? Now what is the next reaction? Next reaction is oxidation. So we have seen reduction, we have seen nucleophilic substitution. You must remember the reagent for the reduction. What we have done it with Hi, that is hydrogen iodide, and what did we get? We get a normal hexane chain. Then further what we have done nucleophilic addition, both with oxime and our cyanide. Now we will see oxidation. What we will see? We will see oxidation. What were the products earlier? Just try to find the names of the product. Okay, so what is the product? This is called cyanohydrine, and this is called hydroxylamine. Why it is called hydroxylamine? So we have hydroxy group here with the amine, so it is called as hydroxylamine, and this is cyanohydrine. So this, if you have studied the nucleophilic addition in aldehyde, ketone, and carboxylic acid, then you must have confronted this type of intermediate. Now next we have oxidation. So for that, what we have taken? We have taken bromine water. What we have taken? We have taken bromine water, and upon treatment of aldehyde with bromine water, this aldehyde gets converted into our carboxylic acid. Now this group that is being formed here can be termed as gluconic acid. It can be termed as gluconic acid. I would suggest you to remember all these names along with this, along with the reaction, because sometimes in the exam you may be asked that give the say this is the product and this is the reactant. You can be asked to give the this is a product and give the reagent, and you may ask to give the reactant, and you can be given the name. So in that case, it would be difficult to do so. So I would suggest you to say remember the name of the gluconic acid. Now, how does this reaction go? So if I ask you how does this reaction go, then what you will be answer? So let us try the mechanism for that. Now, to understand the mechanism, you must get a clear picture of what is the structure of reagent. So we have told bromine water. So what is bromine water? So it is basically bromine dissolved in water. Okay, bromine dissolved in water. Now what will happen? How this will reaction proceed? So we have a nucleophile again, Br2, H2O. Now some of you will tell that why not Br2 and why H2O? Because if you have to do a nucleophilic attack, then the energy levels would match, and bromine falls under very high period, and it is a very high means the lone pair are present in a very high energy orbital. So it would be difficult for the donation, and therefore our H2O, whose lone pair are present, and the oxygen atom since falls in the same period, so it will attack. H2O will attack here. So what will be formed? So I am doing the reaction with H2O right now, and this pi bond will move here. O minus H OH2. Now again an interproton transfer. Now what will happen? We have ROH. I am not mentioning now this H here because it is understood. Now we have O as a lone pair, and we have Br2. Now this will attack here. Now what will happen? Now you would say that yes, sir, you have said that the energy level should match. See, the difficulty comes when your donating species is having the electron in the higher orbit, and your accepting species is having electron in the lower orbit or lower energy orbit. But if your donating species, that is oxygen, is present in the lower and your accepting is present in the higher, then things get easier. Okay, things get easier, not difficult. In turn, they get easier. So what will happen? This will attack here. So you would say that the nucleophile should have lower energy than electrophile. If you want to know the answer of this, why is it so? So you must know what is HOMO and LOMO. So let us keep it for a different talk. Let us just now focus on the key concept that your nucleophile should have electrons in the lower energy, and your bromine, means the accepting one, should have the energy in so have your unoccupied orbital in the higher energy. Now this will attack here. This Br will be kicked out. Will we have Br here and H here, and your OH here. Now what will happen? We have our H here already, as I have told you. So this H will move here, and this will be kicked out. That would result in OH positive Br, sorry, double bond OH. Now it will be deprotonated, and we will get a carboxylic acid. So this is the mechanism that we will follow. So what has taken place? What steps have taken place here? First, the water has done a nucleophilic addition and we got a diol on the same substitute carbon. Although it is not stable, but as soon as it is formed, it attacks the bromine, and next in the next step our bromine leaves with the release of HBr. Okay. Now at last we have a protonated carboxylic acid that is being deprotonated, which gives us carboxylic acid. That will, and the species that will be formed is called as gluconic acid. Now what is the next reaction? Next reaction is a reaction with acetic anhydride. So what has happened in this reaction? We have again our glucose structure. We have reacted with acetic anhydride. The acetic anhydride looks like this. Acetic anhydride looks like this: CH3, CO, CH3. This is the structure of acetic anhydride. So when you react your glucose with acetic anhydride, you will see that each of the OH group has been replaced by this acetic groups. Okay, CH3CO. Now how would have this reaction gone? Now let us consider only one unit. What are we doing? We are just taking one unit. So our alcohol is getting converted into this structure. And what are we treating it with? This acetic anhydride. Now I would give you a second to think of it. How would have this reaction gone? If you have guessed is nucleophilic substitution, then good. If not, then also good. You will still see, making mistakes is very good. So you cannot remember the things which you know more clearly than the things in which you have make mistake. So if you make mistakes, you will remember it for a longer time. So if it is nothing bad in making mistakes. Okay, just try it once, give it a try. So what will happen? There will be nucleophilic substitution. Initially we were adding the OH group or the CN group or the NHOH group. Now we are substituting it. Why substituting it? Because we will remove one group. How? This will attack here. This pi bond will go on oxygen. We will get this thing O here, and we have O minus here. We have CH3. We have O and again CH3. Now this lone pair will come back, and this is a very good leaving group. Okay, this is a very good leaving group. This group is a good leaving group because the negative charge on oxygen is being stabilized on both of this oxygen. So it will be kicked out and you will get RO CH3O. Now again you have an extra proton here. This will be taken by this group that was being released. It will take up this proton and we will finally get O CH3R. Yeah. So this was the group that was we seeing here, that we are seeing here, OCOCH3, OCOCH3. So this is a nucleophilic substitution. Nucleophilic substitution. In which we have substituted our say CO ones of the COCH3 group, this group with this CHOH, this whole glucose. Now we have 5 units of this. Again, this method can be used to identify the number of carbon atoms that are present which are containing OH group. So since it has 5 OH groups here, so therefore 5 moles of acidic anhydride will be involved to form this final product. So 1 mole of glucose reacts with 5 mole of acetic anhydride. Similarly, here 1 mole of this say glucose react with 1 mole of Br2 water. Now next is the oxidation. What is oxidation? In what happens in oxidation? So in oxidation, we have seen oxidation earlier, in which we have converted our aldehyde group to carboxylic acid. Now in this, what we will do, we will convert all the OH group. Since it is also a non-oxidized form, it can also be oxidized to carboxylic acid. So we will convert all of this into carboxylic acid. So we first, this one will be converted. And now if I ask you that we can convert all of this carbon into carboxylic acid or not, so that would be wrong. Why? Because for that you have to break the bond between carbon and carbon. So if I expand the structure in this way, CHO, CHOH, here CHOH, again CHOH, at last we have this CH2OH group. Now if I ask you to oxidize all of this carbon, this carbon, this carbon, this carbon, this carbon to carboxylic acid, then it would not be possible. How? So let me define it with the help of a mnemonic device. So we have a OH group here and R here. Now you have to oxidize this carbon into carboxylic acid. You have put this O, double bond O and OH. Now you can see that the valency of this carbon has been satisfied by the carboxylic group only. Now where you will put this R? This R dash. Means you have to break this bond. Okay, you have to break this bond. So we will not move to the harsh conditions. It can be done. It can be done with the help of harsh condition and strong oxidizing agent. But we will stick to this method only right now, where we will oxidize the, say, our primary alcohol and our aldehyde only. So primary alcohol and aldehyde can be easily oxidized to carboxylic acid. So I will give you a second to think of some oxidation reagent which will oxidize this, say, alcohol directly into carboxylic acid. So you have many oxidizing agent. Just think of one which is strong enough to oxidize this. If you have guessed this John's reagent, then it is true. You can also have KMnO4. This both can be used. So it is basically K2Cr2O7 dot 7H2O. It is a very strong oxidizing agent which can convert our primary alcohol directly into carboxylic acid. Although some steps are involved in it, first it will be converted into aldehyde and then quickly it will be converted into carboxylic acid. Clear? So this is the way we can do it. So if you just treat this carboxylic acid with, say, John's reagent, then this whole thing will be converted into saccharic acid. Now again a new name. So we have seen the see one of those oxidized form, the second oxidized form in which both of the carbon are being oxidized, the upper one and the down one, terminal one. Then it is called saccharic acid. Either you can convert, or you can also convert our gluconic acid to saccharic acid. Here also you can do the same treatment with the Jones reagent. You can convert it into saccharic acid. Clear? Now this were the chemical reaction. So if I ask you what are the chemical reactions we have seen till now, so first we have seen our reduction in which we have used a HI and heated it, and then we got our normal hexane. Then we have seen nucleophilic addition in which we have added cyanohydrine CN group and we have added oxime. Next we have seen oxidation in which we have oxidized our, say, CHO group to COOH. We have not oxidized this group and the group that was formed was termed as gluconic acid. Then we have seen nucleophilic substitution in which we have substituted our acetic anhydride OCOCH3 with our, say, glucose. Clear? Now this is the last reaction. Sorry, this is the spatial arrangement. Sorry for this mistake. This is Fischer projection. Let me write it properly. This is Fischer projection of glucose. So this defines the spatial arrangement of OH group around the carbon atom in the given glucose. Now if I ask you how does gluconic acid look like? So this is gluconic acid. This is saccharic acid. And this is our glucose. During oxidation, what happens? Only this group is being disturbed and been converted into this group, but the spatial arrangement of any other carbon atom has not been even changed. You can see all of these are in the same position. Okay. Now why I am saying this? See, in defining a molecule, we have seen up in class 10, I would say class 10 only, we have only focused on the structure, that what is the connectivity, how is this carbon or this atom converted connected to the other atom. But as you move to higher classes, and for JEE I would say for CBSE also, you should also be aware about the spatial arrangement, that how these connected molecules are oriented in the space, in the given 3D space, whether this goes here or that goes there. So that is a very important point to look upon, because the reactivity of a given molecule is not only dependent upon the composition or the structural connectivity, but also on the spatial arrangement, because certain molecules require certain spatial arrangement to react. So if I give you an example, for that, so let me give an example. Yeah, that would be E2 elimination. So E2 elimination, if you have studied, so E2 elimination requires anti-periplanar structure. Anti-periplanar structure. Now what is the meaning of anti-periplanar structure? So this is the structure of this. CH3. Okay, CH3. Now if I want to do the E2 elimination, then this and this should be, first of all, planar, means on the same plane, and anti, in the opposite direction. So this is upside, this is downside. Then and then only the reaction will take place, or the E2 elimination will take place. So you can see how important is the spatial arrangement for the reaction to take place. This will give us elimination reaction. Now coming back to our topic, so we have seen, so if we oxidize this thing with the help of oxidizing agent, the stereochemistry of the remaining carbon will not be disturbed. Only the stereochemistry of this carbon will be disturbed. I will not say stereochemistry, structure of this carbon will be disturbed, and it will convert into carboxylic acid. Now in the next step, this CH2OH is also converted into carboxylic acid. Clear? So this was the about the chemical reaction. As I have told you earlier, this is the Fischer projection, and you should be aware about each of this position. So this H should be on the left, that it should be on the left. OH, H and H. And this OH should be on the right side, and this OH also should be on the right side. So this is the appropriate structure of glucose. Now when I will teach you more about, means I will teach you a number of, say, carbohydrates, then you will see by just changing the position, you will see that the name of the compound is changed. We have similar chemical formula, but we have fructose, which has the same formula, C6H12O6. Then again we have a next example like our say gallose and mannose. So all of those have the same chemical formula, but the spatial arrangement is only changed. So we have studied all types of reaction, starting from oxidation. First we have seen reduction. We have seen, first of all, we have seen reduction. Reduction was with the treatment of HI and heat. Then we have seen nucleophilic addition. What we have added in the nucleophilic addition? First we have added oxime, that is NH2OH, and then we have added CN. Further we have done the oxidation, I would say with the help of a weak reagent, weak oxidizing reagent. Then we have in it we have converted it into gluconic acid. Then we have done the nucleophilic substitution, in which we have converted our say OH group into acetic group, CH3CO. So we have treated it with acetic anhydride, and in it we have done the nucleophilic substitution. At last we have again oxidation, but this time under harsh conditions. That has given us saccharic acid. Now if I ask you what is the difference between nucleophilic addition and nucleophilic substitution, then what would be your answer? So addition means you are adding something, you are not replacing any group. But substitution means you are adding plus removing one group. So how does it look like? So suppose you have a carbonyl center and your nucleophile is A. Okay, your nucleophile or the attacking species is A. So if you do the nucleophilic, say addition, I'm denoting it with Na, nucleophilic addition, then what will happen? This A group will be simply added here. Suppose this is say R dash. A group will be added and this R dash will remain here only. It will not be removed. Now, if I do the nucleophilic substitution, means you are substituting it. So if you have not heard this term substitution, no problem. So while you have attended class, you must have heard that substituted teacher or our teacher has come in substitution. So that same terminology is present here. Okay. So what will happen in this reaction? So suppose our A comes and attack and remove this R dash. So this R dash leaves. So in this case, what has happened? This A has replaced this R dash. So this was for today's class. We have seen various reactions starting from reduction oxidation to nucleophilic substitution. And we have seen what a glucose is, what is its structure, what are the physical attributes of the glucose. Now in the next class, we will start with the various types of glucose. So we have not still defined the structure of glucose very appropriately, because that is not the actual structure of glucose. It is actually present in cyclic form. And they are present in both form, but the equilibrium is more shifted toward the cyclic form. And how it's that cyclic form formed? So it is just a simple rearrangement, I would say, to give the cyclic form. And again, it will have some structure attribution. So that we will see in the next lecture. So again, I would suggest you that you should be ready with this Fisher projection, because in that class also, in that lecture also, we will be using that Fisher projection. Thank you.